Vinod, now when I click on the custom live service, like on top where it says this meeting is
Yeah,
being,
it's now working.
it's showing the YouTube link. So at
Yeah.
7:30, I guess that will start itself.
So I started now.
Okay. Thanks, Vinod. You can make me host if you want to leave.
Yeah.
Now start admitting people, Rohan.
Yeah, just 1 second, Papia. I just want to fix the view.
What view?
Okay, you can let people in.
I'm doing.
BVR was there also. Oh, wow.
Yeah, many like, you know. Hello everyone for joining the session. We'll start in another 5 minutes. Please wait. So it's 7:30. We just wait another 1 or 2 minutes. People are entering. Then we'll start. Okay, Sarun?
Perfect.
Yeah.
I do hear some background audio.
Background audios. So we'll
Just a request for all participants to please mute themselves.
Hello, Sridhar sir.
Good evening.
Good evening, sir.
Hi, Swarun. Nice to meet you again.
Yes, great to see you again.
We'll wait for another 1 more minute and we'll start.
Okay.
Yes, we can start the session now. So I'm requesting Mr. Sridhar, current Secretary of IITMAA, to give the welcomes to our audience, and please welcome Professor Swarun Kumar. Thank you. It's over to you.
Thank you, Papia. It's my distinct honor to have, or at least initiate this Guru Talks. Today, we have a very young Guru with us. That word carries a lot of meaning, but he has truly, his achievements has truly made him appropriate for us to learn more about the areas that he's working on. I'll briefly talk a little bit about him, and then I'll cede the floor to him to tell you what he's working on. Okay, so Swarun graduated from IIT Madras in computer science in 2010. He was also the PGM there. And after that, he went on to do his PhD at MIT. And in 2015, he got an award for best PhD thesis at MIT. He currently is he's a professor in computer science at Carnegie Mellon. In the ECE department with both computer science and ECE. He works on, he basically designs and builds novel systems to enable faster wireless networks. And his research has impacted a wide range of domains, including wide area networking, wireless localization, RFID systems, and so much more. His research has received 7 Best Paper Awards in a variety of conferences. We're very proud to have him. We just honored him just a month ago with the Young Alumni Achiever Award. We're very proud to have him have this Guru Talks with us. Welcome, Swarun, and looking forward on behalf of all the alumni to hearing what you have to say. Thank you.
Thank you so much for the kind introduction. Is it okay if I share my screen now? Can everyone see it?
Yes.
I think, Sridhar, you're back on mute.
Yeah, I'll just 2 more minutes of your time, if you don't mind.
Sure,
Okay.
of course.
Yeah. So GuruTalks is an initiative of IITMAA that seeks to bring people who are recognized in their fields. These are typically professors. They could also be people who are well known in corporate as well. And through this initiative, what we are looking to have other alumni exposed to cutting edge research and cutting edge practices, both in the corporate world and the academic world. And we have had a variety of really distinguished people delivering these talks. Guru Talks is one of the things that IITMAA does to enable alumni to connect with each other. One of the other things that we also do, in addition to reunions and that happen in December, is we also conduct a conference, flagship conference, annual conference called Sangam. This year, it's happening in Bangalore on July 4th and 5th. I would like to take this opportunity to ask all the people that are gathered here to come and take a look at what we have in plan for you. We have a lot of exciting speakers. So please take a look at our Sangam page and register and join us for the conference. Sorry, Swarun, all yours. Thank you.
Thank you so much. Okay, I'm hoping everyone sees my screen and everything and can hear me fine. Okay, I think I seem to have had a thumbs up, so good. Hello, everyone, and really glad to be here talking to all of you. I saw so many familiar faces among the participants, so it's really wonderful to be back. I was, as Sridhar mentioned, I was back physically for about a week or week and a half, just a month ago. So it's nice to see all of you again. I'm going to talk to you today about my own research in wireless systems and a teeny bit of my own journey getting there as well. I think thank you, Sridhar, for that kind introduction. He already stole my thunder a little bit. I started out not doing wireless at all. I was a computer science grad from IIT Madras, and you see our wonderful building there. Now we have newer buildings too, are all around there clustered. And I was doing hardcore computer science theory, actually, computer security and cryptography. And at some point, when I landed at MIT, my research shifted more towards network security and then eventually to wireless systems. And then I haven't looked back. Since I received my PhD, I've been, since I've become a faculty member going up the ranks in Carnegie Mellon, I just went all in on wireless and wireless systems. And I thought I should explain why and why that is the case. Just to elaborate on the kinds of work that we've done, I lead what's called the YTech Lab, or the Emerging Wireless Technologies Lab. We do all things wireless, ranging from communication, sensing, of course, security, as you know, harking back to my undergrad days, but also a lot of services, sensing, localization, battery-free systems. Now you might wonder, okay, of all the things in the world to do, why wireless? And why is wireless research exciting? And I thought more deeply about this problem. And why should I, or why should you be interested in wireless? I think a bunch of different reasons. First, of course, is the name. It's in the name itself, wireless. It's by definition invisible. Your phone is receiving these invisible signals from some cell tower somewhere, and you're able to see this audio call from me, or maybe perhaps a Wi-Fi access point. And it's so wonderful that all of this communication is happening without anything. And then another exciting thing about wireless is it's tiny. It's in your pocket. It's on in your watch. It's almost everywhere and ubiquitous. A wireless chip is about yay big and costs less than $1. It's amazing that we can enable wireless research, wireless communication so cheaply and inexpensively. And of course, the result of this inexpensive and low cost is, I think, perhaps the most exciting thing about wireless is just the massive scale that is achieved. I know I told you I graduated in 2010. in the 15 years that I've been gone from India, it's amazing how many more people we have connected. At this point, we have more phones than people, not just in India, but around the world. And it's a testimony to the achievement of humanity that we've been able to do that. It's quite exciting. Another reason why wireless is exciting. So if I had to summarize all of these different points in one word, I would use the word pervasive. Wireless is truly the tool to get any compute pervasive, which means it's invisible, it's tiny, it's everywhere. So, but then I went ahead now to really think about wireless a little bit more. And these days, the fad when you want to learn about anything is to go ask ChatGPT or equivalent. So I went and asked ChatGPT, what do you think about wireless? What is wireless? And then here's the response from ChatGPT, not a bad response. It talked about Wi-Fi, Bluetooth, cellular networks, basically wireless communication methods. So in the context of ChatGPT, or perhaps almost everyone on the street, if you ask them, what do you think wireless means? You would say communication. Now, that's not incorrect. That's true. And that is a major application for wireless itself. But my research, at least these days, has taken a broader sort of perspective of wireless, which is wireless is not just there in communication systems. It's so much more. Think about GPS, the system that allows you to track your location, enable not just your navigation, but also apps like Uber and Ola and I guess Dunzo and Porter and all of the other things, right? It's amazing how GPS has revolutionized computing systems as a whole. But beyond that, other applications. So this is, as of last month, the way you get security screenings done at the Indira Gandhi International Airport in Delhi. You are standing in front of a millimeter wave scanner that scans your body. And of course, these systems, if any of you have traveled to Europe or the US, similar systems have existed and are proliferating almost everywhere. And of course, you should not forget radar. I think this is a particularly timely moment to remember about radar systems and how important they are in tracking aircraft and tracking incoming missiles. I remember, it's a particularly important time that we remember that wireless and radar is actually fundamentally a wireless system. So all in all, regardless of whether you're thinking location tracking or security systems or military systems, wireless has been pervasively used for sensing in addition to communication all along. We just haven't been noticing it, maybe up until recently. And its sensing is not just about these niche applications, something broader. It relates to a broader concept in computer science, in electrical engineering, and all of these fields called cyber physical systems. That is, it's not very interesting if computers are just in a box, invisible to us, doing something, crunching something in a data center. Computer systems at some level have to come and interact with us. And if you think about computer systems that can move, you think robots, you think UAVs, you think autonomous cars, driverless cars. So a range of systems that not just sense the environment, but also move along in the environment, but also work with the environment. And the broad term for all of these is called cyber physical systems. There's something cyber about them, there's something physical about them. And if you think about it, any cyber physical system is typically shown by this very simple loop, which is, suppose I'm building a vacuum cleaning robot. It first senses the world, it looks around, it explores the environment, and then it actuates, right? Which is, it actually physically moves. It's first sensing, and then it is moving. And then looping back and forth. Based on where it moves, it then starts to sense. That's why you see this big loop connecting the two. Right? And so what I mean by actuation here is just some way to effectively control. Typically it's moved, but it could also be changed. Some might argue that even smart thermostats are performing actuation. They're changing the temperature of the room based on sensed information. And my agenda today is to really convince you that for all of these cyber physical systems broadly defined, wireless can play a key role, not just in terms of connectivity, the networking aspects, which is a lot of my past research and also very mainstream, but to convince you that there's something more exciting going on in the more core aspects of cyber physical systems, which is sensing and actuation. First, I'm going to try and convince you that wireless can truly make sensing pervasive. Again, tiny, invisible everywhere. And also, I'm going to curiously show you a teaser that wireless can also make actuation pervasive. And I'll explain what that is later on, because I'm going to leave you hanging there for a bit. Let's talk about sensing. So wireless sensing has been around for a while, but if you ask people with a slightly more of a computer science background like me, wireless networking and communication researchers, and if you ask them, okay, what really got you to think about sensing? I mean, wireless sensing has historically been around for a while. It's really in the context of the following. Hey, my phone has Wi-Fi, has cellular anyway. What does it take to make this reuse all of the signals that it's receiving to sense the world, to better understand where it's located, to better understand how to image the world, etc. So can we reuse these communication radios to sense the world? That's really how us people from the mobile world, right, started to think about sensing. But of course, if you take a step back and if you look at like the decades of literature that has existed, wireless sensing is not new. Radar is a big elephant in the room, not just the military radars that I talked about, but even radars in a wide range of applications, radars that are imaging and understanding space, that are understanding the universe, the structure of the universe, remote sensing, basically, systems. And then, of course, the kinds of radars that I talked about in much more classical security applications, like the radars that you find in the airport. Now, if I had to pick one common thing for all of the traditional radar systems that are all shown in this picture, I would tell you they're all big, right? They're all fundamentally large, gigantic. If you picture close your eyes and picture a radar, you're thinking of something big. And here I am talking about things that can be smart, things can be pervasive, can be in your phone, it can be in your watch, etc. It can be in a tiny robot, etc. Certainly, these are not fit for pervasive. Remember, one of the criteria for pervasive was tiny and everywhere. You can't imagine this big monstrosity being everywhere. But there has been a recent shift that's happening. That really happened in the last decade or so, which is the so-called radical form factor shift in radar, which is the so-called tiny radars. So here are a few examples of this. One of the classical ones is as the so-called 77 gigahertz radar or the automotive radar. So if any of you have been in one of the more expensive advanced cars that just magically stop when somebody drives too close, which I think in Chennai traffic might have to stop very often. That is enabled by automotive radars, among other things, and some of course use cameras. And automotive radars are effectively distance measuring devices. They find the distance between vehicles. And then another more familiar example is if any of you have a Google-based Android phone, some of these support gesture-based sensing or tracking, and this is enabled by another radar system solely, which can do simple sort of gesture tracking. And of course, it's not just in phones, it's also in a lot of smart devices, smart speakers, Google Home Assistants, and so on. So all of these are very tiny and chip scale. So then the natural question is, can this be the next camera? Which is, can this be the next camera, but occlusion proof? In the sense that I can have my phone in my pocket and it can still image the world around me, right? So through clothes imaging. I can be a firefighter or moving through a space where a camera is not going to be helpful because the entire room is going to be filled with smoke, but can still see the world because if Wi-Fi can help you receive signals from an access point that's 1 or 2 rooms away, of course, it can help see through smoke. And then can, of course, vehicles and autonomous or even semi-autonomous vehicles help assist driver navigation using in poor weather conditions, for example, through fog. So a variety of applications are possible if radars can be as good as cameras. But then, okay, before I go and convince you with this pie in the sky vision, it takes it's important to first ask the question, wait, I told you in the beginning, these radars are traditionally big. And now these new radars are small. but wait, why did they have to be so big in the first place? Like, when you go to this airport scanner, why is it so big? And the answer is quite simple. It is big because it has so many of these antennas, which are the triangles that you see over there, that are pointing at you and spaced over a large distance. So in practice, at least if you take the TSA scanners in the US, they have about 200 antennas. That's quite a whole lot. So why do you have 200 antennas? Why do you need that? I mean, of course, you cannot imagine something with 200 antennas, at least with this separation, on anything portable like phones. So then you can ask the natural question, okay, what happens if instead of having these 200 antennas, I have fewer? So here's what this 200 antennas buy you. The 200 antennas buy you something called a very sharp beam, which is, if you are having 200 antennas, you can look at a very tiny part of the person's body. Now, this is very important because imagine at the end of the day, you're creating a contour, a visualization of the individual who's standing over there. And so you need very good resolution, very good pixels. And remember, for a camera, wireless camera, the pixel size is important. That tells you how fine or coarse the image is going to be. So here with this 2 meters, you get these very sharp beams, which means you can look at very tiny portions of the body at a given time. And what happens if you compress that into something that's the size of a phone? Now, immediately what you lose is, if you go from 2 meters to 2 centimeters, your beam suddenly becomes very fat, right? So from a thin, sharp 0.5 degree beam, you're gone an order of magnitude worse to a 15 degree beam width, which means it's not going to be a very good imaging system. It's going to be very, very low resolution. So just to give you an example, I have a picture of a floor plan of a typical office space. And the bottom, I have a LiDAR output of that floor plan, where the LiDAR has a 0.1 degree resolution. And on the top, I have this small form factor radar that has a 15 degree resolution. I can see the difference. The LiDAR, you can actually make out this is an office space. It says walls, it's a corridor somewhere. Radar, it's just like a bunch of blobs, lots of leakage, lots of a big mess. Right, so really, really terrible. And that's really what you're getting, not just poor resolution, but also all these artifacts all around. So effectively, what you lost in the small form factor is resolution. So now you're getting this very low resolution imaging. And if you think about it, for a lot of the applications that people have been targeting with these tiny radars, like measuring distance between cars, just doing simple gesture classification, you can still work with this low resolution imaging system. But I think it's a far cry to call this a camera. It's certainly not as good as a camera or a LiDAR system or anything of that sort. So a lot of my research has really been about what would make these tiny, small radar systems something as good as a camera. That is, how can you push the resolution limits of what's possible with these tiny platforms? And we've targeted a whole range of applications, some of which I'm going to talk about, like tire health sensing, through fog markers, through smoke imaging. I'm going to really start with one application that's close to my heart, which is tire imaging. And you might wonder why tires? The reason is this was actually a collaboration that started out with a company called Bridgestone Tires, one of the top manufacturers of tires in the world. So they came to us and asked us, tell us new ways in which wireless sensing could be used to image tires. And you might wonder, why do they need wireless? Why not use cameras to understand tire health, et cetera, Because as you can imagine, tires get very dirty. They are covered in mud and debris and so on and so forth, right? And now you understand why wireless helps, because wireless can image through things. So it can image through mud, it can image through obstructions. So this is a picture of my car with a radar that's taped in the well of the car. So you know this is a student project when you see things like tape, imaging a tire, right? So our broader objective was this so-called tire wear monitoring problem. So any of you owning a modern, more recent vehicle would see the following on your dashboard: a tire pressure monitoring system that tells you if your tire pressure is low. That's available in most modern vehicles. But tire pressure is just one dimension of tire health. What if there's a nail stuck in your tire? What if your tire is just abrased and worn out? It would be fantastic if instead of just a tire tread monitoring system, you had a tire overall health monitoring system. That was really the objective of Bridgestone as well. Right? So you want to know if your tire actually looks like this, and you want your car to alert you, maybe because you are braced into along the sidewalk. So just to scare you a little bit on what happens if you have this will motivate some of you to go back if you own a vehicle to go check your tires. So this is what happens if you drive on a road on a rainy day with fully worn out tires. So can be really, really, really bad. Hope you were able to see the video. So how is this system addressed today? Currently, it's very ad hoc. You have this indirect sensing systems, basically based on tire pressure, or the state-of-the-art gold standard is to go first get a car wash and high pressure wash your tires, and then run it over a laser scanning system to map out the tire tread. So it's not something that you can do every day with any vehicle. So what we instead wanted was something that is compact, that is high quality, that is see-through. As you can imagine, a lot of the requirements that I laid out earlier for wireless in general, and wireless really fits with all of these different requirements. And something that is high quality in the sense that it can measure these millimeter scale variations in tire depth. So our idea is very, very simple. Can we use radars similar to the radars that you have in the airport, right? To image the tires, right? But of course, I've just created this funny cartoon here to show that that's really not practical, right? Can we put a tiny radar, right, now that's looking at the tire and measuring the depth of the tread? And that's really what our system does. It's called Osprey. It uses millimeter wave radars, again, to measure tire wear. And so how does it do that? Very simple. At the end of the day, you can think about how radar works to understand this better. What a radar does is just sends a signal, then gets a response. And then what it does is, think of a radar just measuring distance. When the signal goes and comes back, there's an echo that's heard back. That echo has a delay. From that delay, you can measure distance. And so you can measure distance to different points. So what we need here is something very simple. We need to measure the distance to the surface of the tire. We need to measure the distance to the groove of the tire. And then what is our tire wear? It's tread depth. It's measured by simply the difference between these two distances. As simple as that. That tells us how much tread is left. Right? So how does this work in practice? Very simple. I send a signal. I get these two different time delays based on when the signal reflections are back. And now your resolution is really dependent on your bandwidth. So in this case, I'm just going to throw a number here, that the amount of resolution you can get with these sorts of millimeter wave radars is about 3.7 centimeters. Again, based directly on the 77 gigahertz frequency band and the 4 gigahertz of bandwidth that it occupies. Now, I'm giving this number to just remind you of this one point. Now, this is really good enough because if you imagine the original application for where these radars are used, they're for measuring distance between cars. So 3 centimeter resolution measuring distance between cars is excellent. But 3 centimeters for measuring the surface wear of the tire is certainly not good enough. Because your 3 centimeters is not even going to be in the scale of this picture that you see here. So what can we do to improve this, right? And another problem that happens here is that, remember that I told you earlier that the resolution of the radar is 15 degrees, which means that we are going to see not individual points on the surface of this tire. We're going to see a very large area of the vehicle as well. And that's also not good. So both of these numbers, 3.75 centimeters, not good enough. 15 degrees, not good enough to get any good imaging quality with a tiny radar. So then what can we do? So at this point, it's useful to remember going back to the TSA device. So if any of you have been looking at the TSA device, if you've been to the US and seen this particular device, it has a particular property, which is you stand there in this posture. And then what happens is that of course you get this sharp beam, but also this radar, these antennas are moving around you. They're circling around you. The reason they're circling around you is multiple reasons. First, you get multiple views of the person, which is very useful. And the second, it actually helps improve the resolution, right? This movement actually helps you go from a very thin, very fat pixel along this particular axis to something that is very sharp and thin. So effectively, what you're doing by moving these antennas around is you're emulating or synthesizing a multi-antenna array. This is something called synthetic aperture radar. Again, a terminology I see a lot in the news these days. So our idea with Osprey is very simple. Okay, can we effectively do this sort of synthetic aperture radar? But here the difference is we can't make the radar move around the tire. That's not practical. But hey, the tire is rotating. So in the case of I want you to take a look back and imagine this. In the case of the airport, the radar is rotating around you, but in the case of the tire is rotating around the radar, but effectively it's the same thing. There's relative rotation between the tire and the radar, and that's called inverse synthetic aperture. And that's effectively what we leverage, and that helps us improve the resolution. That helps us overcome some of these limits. So at the end of the day, the end result is that we can get these very crisp images of tires. We can measure height variations. We can measure radius variations. You can get pretty good images showing patterns in the tire. Now, one other thing that we have to measure is the depth of the groove itself. And for that, the way we do it is that we need to be able to tell apart the surface from the groove. And one of the problems with that is the groove itself is featureless. It's pretty flat. There's nothing that tells us to distinguishes the surface from the tire and the groove. So if there's mud stuck in the tire, how will we tell apart the mud from the actual groove? That's a natural question you might have. And so the way we deal with this is leveraging something about how tires themselves are made. So when we started this project, we went to a tire factory and we saw that, and something that I think is in hindsight makes a lot of sense. Tires are not all rubber. They're made of steel, they're made of nylon, they're made of a variety of compounds. Why steel? To give structural stability to the tire. And so one of the easy things that tire manufacturers can do is to inject steel or metallic patterns within the surface of the tires. So here you see a very approximation of that with very thin aluminum foil that has been laid out on the tire. So think about this as a sort of a radar barcode, right? It tells the radar where the groove is located. And so we use these sort of essentially simple, you can think of these as battery-free markers, or you can think of these as barcodes that tell the system about where these grooves are located. And the cool thing about this is this helps the system be resilient to debris. We use a lot of coding literature from communication systems to decide where these are laid out, use lots of different ideas for the choice of materials of these grooves as well. The end result is that we can measure the surface of the groove, the surface of the tire, subtract and measure the depth of these tires. Just sort of a picture showing you of how this looks like in the lab with the tire moving around and the radar measuring these distances. The end result of this is really what helps us achieve the millimeter scale measurement. We're not quite at sub-millimeter, but pretty close at around about a little over a millimeter of error. And in the process, my car also got punished. If you see it on the bottom left, you see my car getting punished with lots of debris being lodged in it and measuring distances as well. So this was mainly what I wanted to talk about. So I'm going to give you a whirlwind of some of the other ideas we have. So one of the other things that we did is, okay, if we, instead of having these barcodes, these barcodes are excellent, but they only work at the short range. What happens if I want to have barcodes not few centimeters away, but several hundreds of meters away? And we build these ultra low power tags that can effectively serve as smart road signs that can talk to vehicular collision radars. That's a system that we developed that can also track where these road signs are related to the vehicles. Just showing you a picture of what that looks like just in an augmented reality application. So here is this ball is telling you where the tag is located. It's actually located inside a closet. Just to, and there the tag is kind of right there on that particular box. Just to show you that this works through not just debris, but it also works through walls. So another thing we did is structural health monitoring, measuring the health of bridges. When they're worn out, we can use a lot of these tags placed on bridges to measure if the bridge is sagging, if the bridge is vibrating, and so on. One of the more crazy applications of these sorts of systems is that we're using these tags and rolling them up with some circuitry, flexible circuitry, into smart pills that users can then swallow, and then it can monitor digestive health by tracking how the esophagus gets inflamed. So we're using lots and lots of cool applications, which is the same concept, we just apply to a few different applications. Again, just a whirlwind, just to give you that it's not just about cars, it's lots and lots of different applications which we can enable. But then I'm showing you point applications. I didn't tell you the general problem of imaging, like what do cameras through obstruction look like? And so this is a system we developed called Radar, which I'm really, really proud of, that really tries to do the following. So, hey, a LiDAR in a smoke-free room would basically capture the room, but the moment there's a smoke, for example, in the case of a fire, the LiDAR would see nothing. Can we make a tiny radar look as crisp as LiDAR? So can we take the terrible looking radar that I showed you earlier and make it actually look like LiDAR? And so I have for some people it might be exciting, for some people it might be disappointing answer to this question. Use deep learning, use machine learning. So we use a super resolution algorithm that leverages deep learning, that leverages deep neural networks. Really inspired by a lot of exciting work happening in the vision community on taking blurry images and making them very sharp. Right? But because this radar data looks very different from blurry images, clearly the picture on the left does not look like a blurry set of walls. It's lots of artifacts happening. We have our own tailor-made deep learning model that spits out that high resolution output and then can be used for a variety of applications. And there's lots and lots of challenges that we need to deal with, like artifacts. So for example, if you look at a blurry lip in an image, it still looks like a lip, but actually a blurry radar data actually creates a lot of ghosts all over the place due to something called signal multipath. So we have to deal with a lot of different techniques for reconstructing the data. So I'm just going to skip through the details of all of that, right? Another problem with radar data is specularity, which is if you look at these sharp corners, sometimes they become invisible because the signals basically bounce off. So all of these different problems exist with radar data and that we need to be really dealing with. So we have a pipeline that essentially takes all of these low resolution data, upsample it into some sort of first downsampling it into a few key features. For example, the fact that in most indoor places you have walls, you have furniture, you have some well-defined attributes. Try and look for those and then upsample. So that's at a very high level how our architecture works. The detailed architecture, I'm just going to refer you to our paper to understand how it actually works. But effectively, it uses for the experts in the room, it uses a UNet-based convolutional neural network to get things done. And there's a whole bunch of architectural choices we had to do to make it work with radar data. But I'm just going to go straight to the results. Here's a radar being put in a smoke chamber, a tiny smoke chamber, because we didn't want to cause a fire alarm to show that it can still image. And just to have a kind of video to show you, in the left is the original radar data. On the right is what LiDAR sees. And in the middle is our reconstruction, just using the data on the left. You can see it's quite remarkably similar to what LiDAR would do. And this is a very tiny radar. And this is this system in the middle works in a smoky environment, unlike the system on the right. And so, yeah, we also benchmark these against the state-of-the-art systems, and it works really well. And I'm going to skip all of these in the interest of time. So many, many more applications that we're interested in: building QR codes, we're doing blood pressure sensing, we're fusing these with vision systems, lots and lots of exciting applications in the pipeline. So watch this space. So I want to close with the second piece of this loop that I didn't complete, which is wireless actuation. So all of these are just lots and lots of examples of sensing applications that we can build using wireless. But what about wireless actuation? And so this is a very cool and crazy project we built. If you recognize this picture here, it's a microwave oven. And you see these LED light bulbs. What these LED light bulbs are showing you is ultimately the design principle of how a microwave works. The word microwave itself is just RF radio frequency waves, right? That operate in fact, the same frequency as Wi-Fi. And what you see here are basically the field distribution of the wireless energy that's inside the microwave. The microwave is basically leveraging wireless energy to heat. And if any of you have used a microwave oven to heat anything, you'll see that if you're reheating a pizza, the pizza's heated in an uneven way, in an unpredictable way. It's a very blunt heating device. So this whole project we started with a very fun project of one of my students who was just frustrated with the microwave oven heating food blindly. And then he wanted to use some of these design principles to heat the food smartly. So both sense and actuate. The problem is if I put a sensor, like anything metal inside a microwave oven, it'll burn, it'll explode, because a microwave is really bad, works really badly with metal. So of course you can put a camera outside, but that really only measures heating after it's done. So if something is damaged, it's already been damaged. So instead, the light bulbs you saw there were our solution, right? Which is we use these modified neon light bulbs as a way to, as a microwave safe way to measure the field distribution inside a microwave even before the heating actually occurs. And the end result is that we can actually see how the wireless is propagating. We see the hot spots, the cold spots. We really understand why the microwave is a poor heating device in the first place. And of course, there's lots of questions we had on where to place all of these different neon lights and so on and so forth carefully so that it captures that field distribution. Okay, but then how do we do the control? How do we do the actuation? It turns out you might think there is actually an actuation system inside the microwave, which is that turntable. When it turns around, you might think it is it is moving the heat around, but it's actually quite primitive. Like this is what the bottom right picture is what even the turntable does. It just smears around those charred hot spots around the space. So we then have a whole bunch of programmable systems on how do we control the turntables? How do we fabricate heat at different parts of the microwave? We have a whole series of mechanisms using embedded platforms to achieve it. So the end result is what you see in the bottom there. We can uniformly heat this wet thermal paper everywhere. So no more charred spots, no more burnt pizza. But more interestingly, we can also fabricate heat structures. On the right, this was a paper that appeared at the conference called Mobicom. So we can literally fabricate heat in interesting shapes just using a modified commercial microwave oven. We can also cook rice way more uniformly than before. So this is again a die that responds to heat, and you see it's a lot more uniform in the bottom row over there. And these days we've gone a step further. We're building these microwave meta surfaces. So no more neon lights, no more complicated systems. Just put in like a meta surface inside a microwave, and that can help you improve the uniform heating. So just imagine you're just putting a metal grill basically inside the microwave, and somehow this helps heat food a lot better inside the microwave. Just showing you an example of how that looks. Student is just taking that, opening the grill. All you need to do is put the grill there, and then voila, that's it, right? Yeah, effectively you can now, the liquid is now going to be heated uniformly. And then the end result is that I want you to just focus on the picture on the right there. You get much more uniform heating than traditional systems, which just tend to heat the surface. So if you've ever heated coffee in the microwave oven, you'd find that the top is so hot, the bottom is really cold, and we don't have that problem. And then we can also heat bread. We can do a lot of other things. You never toast bread in a microwave oven, but we can with our system. But then you might say, okay, is actuation really just microwave? Is it just cooking? Is there anything else to it? I'm going to show you a few more examples. Here's a class of robots called soft robots, and these are robots that can change shape by heating. For example, they can change their geometry, they can even crawl. And traditionally, the heating is done using a using a laser or using a heat gun, and that's very ineffective. Ideally, we want these to be able to crawl through pipes. We want these to be able to move through spaces. We want this to work even with a system that's heating from the outside, but the robot is actually crawling through a pipe. This is exactly what we achieved. Now this is a robot that's actually bending, changing its shape, effectively using wireless heat applied from the outside. We can make these robots fold, and effectively all of these robots are inside like transparent pipes. And here's one more fun application where they have this robotic, think of this as a robotic worm that's crawling through a pipe. And the pipe is again transparent so that you can see it. And effectively it, it crawls through the space with microwave heat that's applied to this film in the middle over there. And just to show you other things that we can do, here's a robotic frog that just can jump by using microwave heating that can be applied. So it's not just about crawling and folding. So hopefully I gave you a whirlwind to convince you that about a lot of the exciting applications of wireless, but I want to thank all of the amazing students who made this possible. I come in and present all of these work as mine, but it's actually tons and tons of hard work of my amazing students over the years. And two of them are actually former IITM students. One of them is now a professor at the University of Washington. The other is working in, as a researcher in Apple. So, but there are many, many more and doing all sorts of amazing work even today. And also a lot of amazing collaborators. If you squint very carefully and scan through, you'll find some IITM colleagues among that list as well. So maybe this is my last slide before questions. Let me conclude with what's really next for this broader primitive for wireless beyond networking, which is wireless sensing and actuation. We're doing a lot more research in the wireless power transfer space. So the dream of, do I have to never charge my phone because my room and my home charges my phone for me magically using wireless, right? That's something we're exploring. There's a lot of exciting applications for wireless heating for health. Cancer therapies today leverage, believe it or not, wireless by applying, using a process called tumor ablation, where the tumor is literally cooked using wireless energy. Can we use some of our technologies to create non-invasive surgeries that can destroy certain cells but not harm other cells by carefully directing wireless energy without actually drilling a hole into somebody? So it's really an exciting and high impact space if we can crack it. But more broadly, imagine all the 4G, 5G, and maybe soon 6G, 7G, etc., right? That's going on all around us. Can we now rethink about this infrastructure, not just for communication, but also for sensing, but maybe also about actuation? Can we think big, that wireless is not just a pipe for communication, but effectively it's just invisible energy. And so something that's readily pervasive, readily tiny, everywhere. And can we make it wear all the hats that it possibly can? So thank you all so much for the opportunity. Happy to take questions.
So much, Swarun. I think I learned a lot as somebody from a non-engineering, background. I just work at IITMAA, but that was very, very informative. So I have a bit of an ignorant question to start us off. I remember reading a lot about the so-called Havana syndrome, where microwaves are being weaponized allegedly in Cuba. What do you have to say about that? Is that even a possibility?
So I want to, first of all, I think it's important to understand the impact of RF on human health, right? I mean, this should be really a question for a doctor than me, but based on the literature that I have understood, at the frequencies, at the level of power that we experience from cellular towers and so on and so forth, that's extremely low. That's several orders of magnitude lower than what you experience from a microwave oven. And honestly, given like the history of AM radio, we've been exposed to it for over a century at this point as humanity. So there's at least a decent literature of data on long-term health exposure of RF at this level of dosage. Now, it's a level of a microwave oven. There's a good reason why the microwave oven has a shielding, has like this Faraday cage, it's called, around it, so that the RF energy is contained within, and any RF that comes out is at a very low level, lower or about the same as what you might experience with a Wi-Fi signal, right? Maybe slightly higher, but not so much higher. So that's the objective. Now, you could you weaponize wireless systems? Like, could you create high energy microwave radiation that causes physical harm? If a microwave oven can cook food, you can of course construct that. There's lots of, I would say some of these are, uh, there was a spy story right there where I'm not going to name the two governments because I don't want to misremember the details, but there was one government that accused another government that their spy agency set up like these microwave emitters around their embassy and caused harm. Again, it's in principle, is it possible to send high energy microwave ovens to cause harm? Yes, it is. Has this actually happened in the past in specific instances? I don't know.
Okay. So I'll go to some of the questions we've got in chat. By the way, to everyone participating, please feel free to post your questions in chat and we'll try and answer them all. Dr. Srinivas asked towards the beginning of the session, some people say Wi-Fi does not have a full form at all. Can you clarify?
So technically, I think one of the versions I call it wireless fidelity, but yeah, it's not clear that it's very widely adopted. Everyone knows Wi-Fi is just Wi-Fi. So I think Wi-Fi, just call it Wi-Fi. It's fine.
Mr. Umesh Chandra asked, so I could use Wi-Fi signals to track your movement in your house. All of our Wi-Fi modems are being imported from China! Exclamation mark.
Great question. Now, I am not going to comment on the China aspect, but is it in principle possible for you to leverage wireless channel information if you have access to that low-level information and some situational awareness? Let's take a very simple example. Okay, does a Wi-Fi device, if I put a blockage in front of the Wi-Fi device that causes signals to suddenly get weaker, can it perceive it? Obviously, it can. It'll see a significant power drop from everybody. So in some sense, even a commercial Wi-Fi device, if you throw the right software at it, already has some level of perceptive ability, right? Some ability to sense the world around it. Is it fine-grained enough to look at individual people, to identify individual people? Probably not, unless you have the right sensors instrumented in it. But is it technically possible to take a tiny box and put sensors in there that can create a high degree of situational awareness about what's going on around you? Yes. Are specific governments doing it? I will not comment.
Yeah, we've been in the realm of sci-fi for a bit, so we'll move on to something that I don't understand. Maybe you can help me a little bit here. Any updates on ghost imaging for indirect imaging, basically quantum entangled imaging? Any new breakthroughs to generate large number of photon-photon pairs?
Oh my goodness, this is like outside my pay grade. So I would say ask a physicist. I'm not a physicist.
Okay, so we'll move on to Mr. Achutan, who asked, can we reach a temperature between 800 to 1,000 degrees Celsius using a microwave? Using microwave,
No.
not a microwave.
Not using a microwave that you get in.
I think he meant using microwaves in general, not a commercially available.
You engineer microwaves to reach those temperatures, absolutely. At those temperatures, you also have to be much more careful about. I mean, it becomes a furnace at that point, right? So you're also much more careful about the choice of materials around the surfaces, right? Like at a commercial microwave the parts would start to melt at those temperatures. So is it in principle possible? Yes, but I have not seen microwaves that operate at such high temperatures. Typically, like traditional furnaces are what operate at those high temperatures. Like, for example, like metallurgy, right?
Okay, and what looks like our last question, unless you guys have some more to post in the chat. Mr. Bova Dutt asks, is there a factor of energy that is key to some applications? For example, would having long-range scanner on an iPhone the impractical due to battery drain?
Okay, I need to. Can you repeat that question? I didn't fully get it.
I'll just repost it in the chat, but I'll read it as we go.
Okay.
He says, is there a factor of energy that is key to some application? For example, would having a long range scanner on an iPhone be impractical due to battery drain? I'm assuming he means a long range radar scanner or something of that sort.
Good question. Yes, there is an energy toll on all of these sensing systems, but for the single chip radar that I talked about, it's very much something you can integrate on devices. Obviously, there's going to be a battery drain to anything that you add, but it's not substantial. And I don't have the precise numbers with me, but I'm just going to give proof by example, like unscientific. Google has had solely on some Pixel devices for a while, and that somehow seems to work fine. I've not seen complaints about solely particularly draining the device battery. So it's in principle possible to do it. Now, of course, the numbers matter. If you're boosting the range to something very long, if you're boosting the resolution, if you're running a lot of, a machine learning pipeline to do reconstruction that is heavy in terms of compute, you can cause more battery drain. So there the numbers start to matter. But is it in principle possible to integrate a tiny radar on these? People have already done it. So that tells me that, okay, it's not like a no because of battery.
Okay, I think this should be our last question, maybe one more after this. This is from a student, Sriram, at IITDM Kanchipuram, from an ECE background. I think you answered this in your talk, but maybe he missed it. But his question is, can we use microwave to cook tumor cells using metasurfaces, which can change form? So I think you
Yes.
talked about this.
Yes, that's something we're actually looking at. It's really hard to get this right, because I think cooking the tumor cells is not hard. Not cooking the regular cells is hard.
Yeah.
So making sure that we use this. So if you're interested in how it's done today, effectively, I know this may be graphic for some. You drill a hole, and then you take in an antenna, probe it deep down into the tissue, and then you, of course, need to know exactly where the tumor is placed, and then you blast energy at one specific point. Now, this is still a lot less invasive than doing an open surgery, where you're opening it up, using surgical utensils to find the tumor and taking it off, right? Or, also more specific than chemical treatments. But still, you need to drill a hole and go down there. In our world, it would be fantastic if you didn't have to drill a hole, if you could just use antenna placement, just like you might get a scan done. Can you actually get the tumor ablation done? It's really, really hard to do it though, because it's hard to make sure you hit this one point, but nowhere else. That's really a technical challenge.
All right, and I think we close with this last question from A. Kumar. What are your thoughts on wireless power transfer over longer distances, typically more than a meter, while maintaining high efficiency? Is the plan to use magnetic repeaters to achieve this?
So there have been people who've already done it, typically using magnetic resonance coupling between effectively, like, think of this as a glorified, like, the wireless power transfer is like reinventing the transformers and reinventing inductive coupling and so on and so forth, right? So that's basically what people have done to make sure that you can transfer over a meter. The problem really is multifold. There's a lot of energy loss that happens. You need the infrastructure in place to get it done. The one application I think is going to happen very quickly is charging stations for EVs that do not require you to plug in anything. I think that is something that is certainly going to require more than you need to go from centimeter scale at least to something tens of centimeters. And I think that is an advance that is more short-term likely for high energy charging applications. For charging phones from your far away base station, I don't think that's going to happen anytime soon, but smaller IoT devices is very much a possibility.
All right, thank you so much. I think that's it for today, but I would like to extend my thanks personally to all the participants who joined us and to you for taking the time. Now I really regret not being in Chennai for for your YAA award. Would have loved to have met you in person. Papia, over to you to conclude.
Yeah. So thank you, Rohan, for moderating. And Sarun, I just want to let you know, when I will send a thank you mailer to all our participants, if they have any questions, I will direct that questions to you. Is it okay?
Absolutely. Wonderful.
Okay. Thank you.
Sorry,
Thank
one
you
last
so
thing to
much.
add. Some of you did ask for contact information. Please email either Papia or me or shoot us a WhatsApp, and we'll be happy to
Yeah.
forward that to Swarun, and he can get back to you directly.
Yeah, due to our privacy reason, we are not sending the contact details of alumni to all, but definitely through us, you can get in touch with the speaker. Thank you everyone
Thank you all.
for your time. Yeah, thank you, Sharun. So we can close the event. Thank you.